Hello, I'm Stephen Collins, and today I'll be walking you through how to solve for the efficiency of a simple gas turbine engine. Gas turbine engines work by first drawing air into the front of the engine where the compressor is located, which then increases the pressure of the air as it flows into the engine. Next, the pressurized air then passes through a combustor where fuel is added and ignited, raising the temperature and pressure of the gas even more. Finally, the high-pressure, high-temperature gas flows through a turbine, which spins as the gas flows over the blades of the turbine. This causes the shaft of the turbine to spin, which in turn causes the compressor to spin and allows for the continuation of the process. The spinning of the shaft can also be used for work or to power a drivetrain. The exhaust gases coming out can be harnessed and used as thrust to provide propulsion for a vehicle such as an aircraft. There are many examples of turbines in everyday life. For example, there are ones that are specifically designed and used by the military in jets or airplanes. There are also jet engines developed for commercial airliners to get people from point A to point B as efficiently as possible. And there are even ones that produce the electricity that lets you turn on the lights at home. Now we are going to solve a basic efficiency problem for a gas turbine engine. Let's say the inlet temperature at the compressor is 300 degrees Kelvin. The compressor pressure ratio is 8, and the temperature at the turbine inlet is 1300 degrees Kelvin. Using the air standard assumption, we are to find the thermal efficiency. The efficiency of a gas turbine is calculated by dividing the net work by the heat transferred into the system, Qn. Net work for a gas turbine is the work that the turbine produces minus the work the compressor requires to run. We can find the work done by the turbine, the work done on the compressor, and the Qn by finding and using the enthalpies at each of the 4 points specified on the diagram. Given that the temperature of the gas entering the turbine is at 300 degrees Kelvin, we are able to determine that the relative pressure measurement at point 1 is 1.3860, using the chart A22 in the thermodynamic appendices. These appendices will be used throughout the solution to this problem, and if you do not have them, they will be posted at the end of this video. Next, we are able to calculate the relative pressure at point 2 using the compressor ratio and the relative pressure at point 1. Given that the compressor ratio, represented by R, is equal to P2 over P1, and using the properties of an ideal gas, we know that the ratio of relative pressures at point 1 and at point 2 is equal to the ratio of the actual pressures at point 1 and 2, which we know is equal to the compressor ratio. Using our value for relative pressure at point 1 in our equation, we are able to solve for the relative pressure at point 2, which is 11.088. From the principles of isentropic processes, where change in entropy is equal to 0, we are able to deduce that P2 is equal to P3 and P4 is equal to P1. Using the compressor ratio and substituting the appropriate variables in for P1 and P2, we are now able to get the turbine pressure ratio. Again, using the principles of ideal gases we use to relate the pressure ratios at points 1 and 2, we can deduce that the relative pressure ratio at points 3 and 4 is equal to the actual pressure ratio at 3 and 4. Now using the same appendix chart as earlier, we see that the relative pressure at point 3 is 330.9, when the temperature is 1300 degrees Kelvin. Now we can find the relative pressure at point 4 after rearranging the equation of relative pressure and the turbine pressure ratio, and we find that the relative pressure is 41.3625. Using our relative pressures in the chart, we can now find the enthalpies at the 4 points that we will use to solve for the efficiency of the system. From our chart, we can easily find the enthalpy values at points 1 and 3, 300.19 kilojoules per kilogram, and 1395.97 kilojoules per kilogram respectively. However, for the enthalpy values at points 3 and 4, we will have to interpolate to find these values. Using the formula for slope of a line between 2 points and our given relative pressure values, we are able to calculate the enthalpy for point 2, 544.18 kilojoules per kilogram, and point 4, 789.39 kilojoules per kilogram. Now substituting our enthalpy values into the equation we derived earlier for thermal efficiency, we can calculate the efficiency of the gas turbine to be 42.6%.